In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister
All right, hello and welcome everyone. Tonight we're going to be doing a presentation over at Earth Awakenings. But before we get into that, I wanted to say thank you everyone for the continued support. It means a lot. You guys are crushing it. The limited edition hoodie sale ends Tuesday. So if you guys are planning on getting a hoodie, that runs on Tuesday, that ends on Tuesday, and those will never be available again. Now the hats and shirts will be still available. That'll be a primary thing that'll be in the shop, but the hoodies will disappear. So if you were waiting to get a hoodie, get one before Tuesday because they are going to go away. All right. We are going to get into the Earth Awakenings presentation now. So here we go. Just give me one moment. Greetings, lads and ladettes. Let me go ahead and start the screen share here. Okay, you guys see that okay? All right. So I got a couple of assorted notes to go over and kind of like a timeline, I guess. So the other night we were talking about GPS, and it was asserted that through timing intervals, meaning space vehicle to ground receiver, you can measure the z-axis of that, and that gives agreement with globular dimensions, meaning that you could measure the globe through timing differentials to assert ground measurements. And we were saying that first of all, the speed of light isn't constant, and there are corrections on the back end that are made to give the appearance that the speed of light is constant. And because of those timing offsets, you can't trust the reliability of the overall system because the back end could be completely correcting for something different, and the signal output would be basically cooked to present itself in a coordinate system that the receiver would use with those timing offsets, and everything would appear that it's working with different dimensions than it actually is. And all of this is done through timing offsets. So to make the speed of light appear to be constant, you use timing offsets to derive distances. To derive this z-axis distance from space vehicle to ground receiver, you use timing differences. So if they're correcting timing differences and the speed isn't constant, then we need to understand that we can't use that system reliably, right? Because that's what's in question with those measurements. So there's a couple of things I wanted to go over with that. So one of the things that Taylor pointed out that I'll read here from, we'll go over her notes first, starting with GPS signals going, measuring that timing interval to the z-axis and what they say about the post-processed calculations and things on the back end. So this is from geoweeknews.com, and the link is right here. So further, the ends of the baseline determined by the GPS observation are typically given in ECF coordinates so that the vectors themselves become the difference between those x, y, and z coordinates. The display of these differences, dx, dy, and dz, is the usual product of post-processed calculations. Now, what they'll tell you, or what's asserted primarily through the GPS argument, is that we're just the ground receiver. We're just using this raw, the quote unquote, this raw measurement. Right? Without this, we're not doing any special corrections on the back ends. We just have our receiver. So people aren't aware that what is being sent to them is already cooked out to give them the exact dimensionality of what they need. And we'll get into how they make these corrections on the back end here. But this is just asserting from the processing point of like before the signal is even sent out from the quote unquote space vehicle. Right? I just say space vehicle because that's what it's referred to in all the manuals. They call it the SV. All right, so this is from esri.com. Cartesian coordinates. The GPS receiver can provide only the ellipsoidal geometric height. Consequently, newer GPS devices orthometric geoid height or output the orthometric geoid height measurements as a product of behind-the-scenes calculations based on a combination of formulas, tables, matrices that help use geographic coordinates as inputs. Oh, no way. So they're making adjustments to time, to the time of flight for the speed of light to correct for different elevations according to different geoidal models, which is what we're going to go on to read here. So the appropriate height of the geographic location taken from the coarse or fine DEM matrix is provided instead of the real measurement of the Z value or height. Oh, no way. So these aren't raw measurements in the way that it's asserted. Now, this is just a product of what the system is. And especially under the current paradigm where the speed of light is asserted with constancy, this has to be like these back-end corrections are necessary. Some receivers use approximations of the geoid height to estimate the orthometric height from the ellipsoid height. Still, other units based on the older technology provide direct readings of the Z value based on the ellipsoid. All right. That one. So now we have what is this one? The graphic here. I think this is the one where they take two different geoidal model differentials. All right. So the raw GPS height expressed relative to the WGS 84 reference ellipsoid model of Earth. Okay, so they take this measurement, and if it's plus or minus, they subtract time from it. This value is then converted into the express height of the local mean sea level, or mean sea level, specified in the WGS 84 using the EGM 96, the Earth geoid model. So they're taking two different gravitational geoidal models here, and quick refresher on what these are, right? Because a lot of people, if we Google this here, what are we gonna see? What are we gonna see when we Google this? Where's the oh, they don't have the I'm looking for the gravitational heat map image. It looks like this one, but it's wrapped on a ball. This one right here. But oh, this one. There we go. All right. So we see this geoidal model here, and one might think that the Earth is shaped like this or whatever. This is a representation of the gravitational strength potential at different areas. Now, how did they determine the gravitational strength at these areas? Well, this was done through astrogeodetic surveying. So if you guys have ever heard of the arc of the parallel, where they took horizontal measurements across they basically just made triangles across the United States and made and then compared those measurements to positions of the stars, and then made corrections based off of Venus transits, eclipses, etc. Right. So anyways, whenever they would do trigonometric functions and then reference stars, they would traverse the land and then take zenith measurements of the stars. So they would traverse the land, take their telescope, look up, take a zenith measurement, and when they looked up, they found that there was a deviation from where the star was expected to be. So they took that difference, accumulated them all, and that difference is the quote unquote that's the reference ellipsoid, right? That's the foundation for that. And then when they came back around and took measurements, they had to correspond the locations on the ground to these positions on the stars, right? But they were off. So what they did is they said that their plumb bobs, when they were taking measurements, is actually deviated even further than it was due to the reference ellipsoid. right? And that there's a gravitational anomaly in these areas, so that the plumb bob is physically deviated and it's not going straight down to the center of the ball. It's actually offset. So that's creating a further deviation. So they're saying, like, if you ever heard like level isn't level or whatever, whatever that means, that's the mindset that had to be introduced to make these sky observations comport to the ground observations. So this entire geoidal model is constructed from that. It's constructed from that. So that's what we're referencing here when we're talking about these gravitational models, right? So this isn't like somebody was out there measuring gravity or anything, right? This is optical deviations of positions of stars and then trying to get the ground to line up to that, right? This isn't this. So like, just to be clear on what this is. And then so now they've got this system, they've got this model, they've got these dimensions, and they've got this GPS system that's at some elevation above us, right? Sending signals down. So now they have to make the timing intervals comport to wherever they need that altitude to be for that craft. Now, these back-end corrections that we're referencing, right? These are all things that would facilitate the mechanism that would make the outputted signal comport to these dimensions so that a ground receiver would be able to get useful information relative to where they are on the coordinate system, right? And this is all based off of the timing differential for whatever you need the altitude of the space vehicle to be. You can make it comport to whatever you need to be at any altitude with timing offsets, because all you have is just a signal that's being set out with a frequency to it. You could offset the frequency, you change the interpretation of the timing, and that's it. All right, so I think we have, we went over all of that. There was one additional thing I wanted to cover, or a couple of additional things I wanted to cover. Okay. One second. Okay. Close that. Okay, the first thing is, if those, let's say that gravitational model is correct and those potential differences are there, right? Well, experimentally, it was measured that in the 1960s that electromagnetic frequencies going vertical, right, even from a difference of 75 feet, will experience a frequency shift due to the quote unquote gravitational potential. Now, if there's a non-uniform gradient, right, if there's these anomalies such that it creates areas where your plumb bob is deviated and you have to make these corrections, then also there will be latitude dependent GPS corrections and longitude corrections for gravitational potential offsets for the general theory of relativity. Now, what they actually make is what they claim to make anyway, is one uniform correction. And they say that basically the way that you can conceptualize this is that there's a stationary gravitational field created by the Earth that's fixed to the Earth, and the Earth spins through that. But they conceptualize the Earth as being oblate. So the oblateness and this rotation offsets the gravitational potential difference at all locations and makes it a uniform gradient. Now, whether or not that makes sense to you or not, that's what they say.
What?
So, yeah. So in GPS, they don't make any corrections like they do on the ground when they take measurements and they say that their plumb bob is physically deviated. Like a physical object is not that's hanging to the ground, isn't actually going to the ground. They've determined, right, via position of stars because of gravitational anomaly. But an electromagnetic signal sent there experiences no retardation or velocity addition. Well, no, it would receive retardation because it would be going into the gradient, but it receives no retardation in frequency in those areas that needs to be accounted for to the magnitude of what they're asserting is causing the deviation of their plumb bobs. It's completely contradictory. So we have this here quote is from A.G. Kelly, but we have quotes from Ron Hatch explaining the same exact thing. I have some from Neil Ashby, who's like the main GPS relativistic fixer for the mainstream.
Quick question.
Yes.
So you're saying that basically they say that this gravitational potential affects the starlight, but not the light of the satellite or anything else. So it,
Ooh,
it bends
ooh.
starlight, but it doesn't bend your signal because it's uniform somehow.
So doesn't bend the starlight. It bends the plug bob on the ground, and it makes you think that you're level, but you're not. To get level, to get that star where it needs to be, you have to tilt, right? But then when they send electromagnetic signals in the same spot, there's no additional gravitational frequency shift that's measured there, even though at the levels that they're working with, like if it would be sensitive enough to have a frequency shift. If it's going to deviate a plug bob, I mean, it's going to change the frequency of light. So so anytime you hear about the geoid or gravitational potential or my plug bob, well, reference GPS corrections that don't correspond to their asserted gravitational anomalies. So let's see, there was one more thing here. Okay, so there's 3 important GPS corrections that we need to go over here. So this is from A.G. Kelly as well, who is citing from different manuals and 2 institutions that he wrote to regarding the corrections, because there's 2 corrections that are said to be relativistic. Well, there's 3, but one is it's a weird correction that's not, you wouldn't really call it relativistic. So anyway, here we go. So both bodies name 3 corrections as relativistic. These are the velocity correction calculated under special relativity or when transporting the clock. So this is actually, non-reciprocal time dilation. So in other words, just retardation proportional to the velocity, otherwise known as the Sagnac effect. This isn't a relativistic effect. This is a classical first order effect. And the correction for it is actually just V over C. So we'll continue on here. It's phrased in the way that, and it's interpreted through the relativistic lens or whatever, but it's actually just the classical effect of retardation proportional to the velocity of the moving clock. Now, for it to be a relativistic effect, right, the old stationary clock on Earth would have to miraculously somehow also show that it experiences retardation proportional to the velocity of the clock that is moving around it. Now, I bet some of you were like, that sounds retarded. Why would that have to be a thing? Well, relativity is based on mathematical reciprocity for transformations. So if you don't have reciprocity for transformations, then your frames aren't equivalent. And if they're not equivalent, then one is preferred. And if one's preferred, then the theory is bankrupt. So the fact that they've only have one-way time dilation measurements and never the reciprocal should be a big indicator of, how correct the theory is in terms of is asserted time dilation of a atomic clock a quote unquote relativistic effect? Well, no. The correction for the difference in gravitational potential under the general theory outside of the scope of this paper. So Kelly was more talking for special theory stuff. But anyway, this general theory gets into the gravitational potential, right? So when they talk about elevation above sea level, right, that's where the gravitational gradient is going to change. That's where the clock is going to run faster because there's less gravitational potential to cause the retardation. So they offset the clocks, they say. And then when they get to altitude, they will run faster because they started them retarded a little bit. So that's one of the things that they assert there. And this is the uniform correction, right? So remember how if there's some anomalous action in the field that's going to shift the frequency of light as measured in the 1960s and 1965 by Pound Repka and Pound Snyder here, who won the Nobel Prize for proving the correctness of gravitational redshift with the general theory of relativity at a elevation difference of 75 and 70 meters respectively. These should be accounted for. So to kind of give you guys an overview of what this would look like for general relativity correction here, is that they're saying this satellite, as it's coming over the Earth and sending signals out, well, if there's an observer here, and this is one of the areas that has, quote, all these gravitational anomalies that are tilting these plug bobs, this satellite here is going to have to correct for this. There's going to have to be some timing correction here, some latitude dependent correction and longitude. to isolate this anomaly here. Yet they use a uniform correction here. So we'll continue on. We're almost done here. Let's see. The latter correction is the Sagnac correction. It has nothing to do whatever with relativity. Now, that one was also the Sagnac correction from the movement of the atomic clock. But here, this one is saying from the, like if you were to send a signal from a space vehicle, right, from a satellite to the ground, and the person's stationary, they're saying it would be off by a little bit unless you make this correction here. And they're calling this the Sagnac correction under relativity for Earth rotation. In other words, the timing difference is created because you physically moved in location, either closer to the signal or further away. So the latter is the Sagnac correction. It has nothing to do whatever to do with relativity. It is the correction necessary because light does not travel around the globe eastwards and westwards at equal times. Now, obviously, you know, lad's a globularist. Well, GG, he believes in a globe, right? We can pack up the whole thing. That's obviously retarded. There's an east-west bias, right? For these for electromagnetic propagation, right? That measures sidereal time. Some people say that this is Earth rotation. We assert that this is an ether mechanic function of the rotation of the sky being measured via ether wind. So this timing offset is it's not mutually exclusive. What would be mutually exclusive would be north-south timing differentials, because physically, if you're on a ball, right, it doesn't matter if you're north-south or east-west. Like, in other words, if you're moving with the direction of motion or against it or perpendicular to it, you're still physically going to be in a different location. And there are no north-south timing differentials that are measured. So, in other words, it's as if the object is in the same spot from when the signal was sent to when it was received, and it's not receiving any of this east-west differential. Now,
that's wild.
On a globe, that's physically impossible, because it doesn't matter that you're physically in a different spot. If that's the explanation, then there has to be north-south differences, and there's not. So this leads, now this doesn't give a mutual exclusivity to globe or flat Earth, right? This is just a light bias correction, right? So what this does indicate, though, is that the Earth is stationary and it's not moving, and that there is something carrying the light around that follows sidereal time. All right. Now, the interesting thing here is that Kelly writes out to two different institutions that are in charge of what is it called? Like the protocols for synchronizing atomic clocks. And then they talk about this Sagnac correction. And this Sagnac correction isn't a relativistic correction in the sense of link contraction or time dilating. What they're doing is called a coordinate system rotation. So if you look at let me see if I have a quick diagram here. Oh, nice. I got coordinate systems. So if we look at this, if you just look at this X, Y, Z here, right? If we imagine that this Z is time instead of Z, and this Y is an X, so that this is perpendicular to the other one right here, left to right. What they're asserting mathematically is that they're transforming the time component, and they're moving it here, and they're moving the distance component, and they're moving it here. And they're saying that that is accounting for Earth rotation under a relativistic transformation. That doesn't make any sense. So whatever that is, right? That creates, now, is that a timing offset? Good question. Now, if they don't correct for this, if Eric's still here, he can attest to this because he's a GPS receiver programmer. But if you don't account for this rotation here, this coordinate system rotation, then GPS will be off by 30 meters to the east, I believe, if I'm not mistaken. And so, although it's not a direct add or subtracting to the timing of flight, the rotation of this creates the desired effect where the offset corrects the 30-meter difference. So that is the extension of relativistic corrections as asserted by the mainstream in GPS. And then we have, let's see, I think that was pretty much everything. Let me go through here. So a quick refresher on the postulates of relativity and why this is an issue, and why once you know about the timing differences, you can't trust the source, right? You can't trust GPS as a reliable witness because it's corrected in a way that you can't control or ever do anything about. So Einstein's postulates, the laws of physics are invariant to an observer in different inertial reference frames. So if you're stationary or if you're moving at a uniform constant velocity, the laws of physics and the way you perceive light should be the same for everyone. And the speed of light is the same to all observers regardless of their relative motion to the light source. So moving towards or away, there should be no differential in the timing of the speed of light from source to receiver. So this is where we get into problems with the Sagnac effect, where we have a source and receiver fixed to a platform rotating. There's no relative motion between them. They're both fixed. They're rotating at the same distance apart. Yet there's a first order fringe difference produced, right? So same situation is going to come out of this because GPS signals are one way, right? Space vehicle to ground receiver based off of a timing difference of a absolute timeline, because GPS functions off of establishing GPS time. So maintaining a synchronized timeline for all these signals to be relative to, that's how the back end of all this works to derive these distances. So if all this works under relativity, you shouldn't be able to measure someone's velocity directly proportional, right? Because if they're moving at a constant speed or if they're stationary, then there should be no difference because they're in an inertial frame. But yet GPS, what we're going to find is that it measures the velocity down to the millimeter, basically down to the wavelength. But the wavelength that they use is, millimeter. But if they could go further, it would literally be accurate down to the wavelength. As long as your motion, the distance you travel, is bigger than the wavelength, it can be measured. So with light. So anyway, this is regarding transformations. We can skip that. So another interesting thing for relativity and stationariness, right, and the preferred frame and all that. This is kind of supplementary to anyway, this is not necessarily related to shape or anything like that, right? This is just an interesting little issue for them. So they assert that these GPS satellites are in an elliptical orbit and they should have an acceleration deceleration timing correction for their clock bias, because remember, they're experiencing time dilation, or quote unquote, I'm using air quotes here. They're experiencing time dilation relative to the stationary stations relative to the stations on Earth, and they're going to have to correct for this. But because relativity theory is true, right, and the Earth is not a preferred frame, well, if you were to transform to, I don't know, Mars and look at this satellite system orbiting Earth, what would it look like? What would it look like? Well, it wouldn't look like an elliptical orbit. It would look like this. It would look like a cycloid, where it goes in and out like this. So ignore the red line for a minute. Let's just look at the Earth. Earth is moving this way, right? It's going this way. There's a satellite going around it as the Earth orbits. This is what it looks like from our perspective, right? Now, if you were in a different reference frame, anywhere in the solar system, it would look like this. So what we must see is an illusion, and otherwise it's a preferred frame. And the real corrections of an atomic clock would look like this acceleration deceleration period. It would have this cycloid nature to it, not an elliptical acceleration deceleration period. And what do we get? It's a acceleration deceleration correction. So we don't get the relativistic, no preferred frame. It would look the same everywhere. Therefore, what we're seeing is an illusion frame. We don't get that. We don't get that. In reality, this satellite corrects for accelerating, decelerating, creating that elliptical loop. So it's circling above or around us, depending on your cosmological belief. But it's not going around a ball that's moving around a solar system and then like under the correct presumptions of relativistic effects. None of that's manifested. The clock would literally have to have different corrections. It would be one of the most profound proofs of relativity theory if they sent the clock up and instead of acceleration, deceleration, they had to accelerate, or they had to decelerate, accelerate, and decelerate. And like that it would just be amazing for them. But it's not. It shows that that this is the preferred, that the way that we're looking at it is the only way to interpret this. Now, the same issue that this cycloid applies to, like the same issue that this is having, right, is it occurs when you do the Sagnac effect with a rotating interferometer. So if you try to do the relative motion between the source and receiver via transformation of the source and the receiver, the path is going to look like this. It's going to look all messed up. It's not going to make a circle anymore. So that's why they have to invoke the preferred frame and all these things. So this is showing that the correct way to interpret this is that the Earth is stationary and the satellite is moving around us. Now, another fun fact is that if any of these velocity vectors were real, right, the atomic clocks on board, when they're parallel or perpendicular to the directions of motion of these, would have to be added to, right? But none of those are manifested either. And then a quick recap on how an atomic clock works, so we can understand what an atomic clock is even doing and what a correction of it, what it means to correct for. Which part of this corrects for general relativity, which corrects for special relativity, which corrects for the Sagnac rotation or whatever, right? Well, let's see what we got here. So this is a diagram of an atomic clock. We have a cesium oven that's going to emit cesium vapor. It's going to go through a little collimator as it leaves the oven, and that's going to send it into a coherent beam where it enters a magnetic field where it's oscillating at a certain natural rate. Any cesium that's, excited due to the heat or whatever, or not excited enough, it lost some energy, it gets ejected due to the magnetic field strength. So if it's not in alignment at that specific oscillation rate, it gets ejected. Then it enters this chamber here where microwave signals are sent into this chamber, and it bounces off the cesium. And once the oscillation rate of the cesium matches the oscillation rate of the microwaves, they introduce this the C field here, which is just another magnetic field, which helps them lock in the proper frequency once they get everything adjusted, because this thing is very sensitive to motion and drifting, etc. Different spikes in readings or whatever. So like it'll just retard, or it'll just increase in reading or whatever occasionally. So anyway, this is another field that helps modulate that. And then once they have this frequency matched up, it leaves the chamber through another magnetic field that ensures that as it's leaving, that it's matching this same frequency that it came out of here in. And then it hits this ionizer where the energy from the gas in the microwaves gets ionized, and it hits a electron multiplier, which is basically just multiplying an electric signal off of mirrors back and forth. And then they're converting that to an electric signal. And that pulse rate of that conversion is giving them the 9.192 gigahertz oscillation rate. So that this is splitting 1 second into 9,192 millionths of a second through this process. Now, that number gets a little lower when the clock is moving. So they have to introduce a little more energy to offset that reading. That's all it means to retard the clock or correct it. They're just like changing the interpretation of that rate through introducing more energy or reducing the amount of energy that they're using to offset. So that's not like there's a special thing in here. So anyway, we have two different values, right? We have a gravitational potential value and we have a relative velocity value, and we have a quote unquote Earth rotation and or ether drift value. Now, the offset for the velocity and the gravitational potential is the same mechanism, right? It's just it's just in magnitude of the adjustment for how much energy you're going to put in or how much you're going to subtract if it's accelerating or whatever, right? Or receiving that velocity boost. So that's the basic breakdown of that. And this helps maintain the constant timeline. And then GPS sends out signals based off of this. So another interesting thing to note is that when a space vehicle or a satellite carrying these atomic clocks crosses a meridian line, there is a signal that is sent to it to give it a timing correction. So this gives it an offset, which changes the time, which would literally change its position, right? Because if you change time, you're changing distance in this system because the distance is derived from timing intervals. So as these stations move across the Earth, globe or flat, the timing is being adjusted on them to make them appear as if they are in the exact location that they need to be so that you can use the system so that it's useful to the latitude longitude system. And this, I wanted to point out, is not necessarily malicious. It's not a bad thing, right? Irrespective of the east-west differential and the stationary or motion of Earth, etc., right? All of this, like these timing corrections to keep the system unified to work, it would all be necessary anyway. And the fact that they are, shows that relativity isn't the correct interpretation. But I'm saying like the timing difference adjustments to make everything work and stuff isn't malicious per se, but it does make it so that as a GPS receiver, right, you can't know the true altitude of the satellite. You can get signals that are timing offset that you interpret as that distance, but you can't know for sure because you can't know where this atomic clock is really at because you don't know the meridian correction that was applied to it. All right. And there was one other thing regarding the velocity of the receiver. See if I have that and we're good to go.
Can't just be the timing difference, huh?
No. All right. Well, oh yeah, here it is right here. So this is from Navstar GPS User Introduction, 1996. So it says here, the Doppler shift of the frequency of the received carrier signal is proportional to the relative velocity of the receiver with respect to the satellite along the line of sight from the receiver to the satellite. So this is a first order timing difference in the speed of light. Now, they'll say, well, relativity is true and the speed of light, or the wave change is inversely proportional, the frequency and the wavelength. So, but the speed is still the same somehow. That's inadequate. The distance is derived from timing difference intervals. If there's a Doppler shift, then there's also a timing shift that corresponds. Otherwise, the distance, that's insane. So it's all like you can literally measure the same exact thing with an interferometer. A closed loop beam going clockwise and counterclockwise is the same kind of one-way measurement once it recombines. Right, it produces two different timing differentials that produce the fringe. Go ahead.
That the Earth would be like a Sagnac device?
Not only am I saying that, I'm saying that the range measurement equation itself can actually be used to derive the Sagnac effect. And that was actually shown by Ruyong Wang, which we can close out on. All right. Don't judge me for my gross misuse of the highlights. But here we have the range measurement equation. The time that the receiver signal was sent, the time that the signal receiver was received is equal to C times signal time received times minus the time that it was sent. Now, what this means is, like this, you look at this and you're like, oh, well, they're not adding or subtracting to the speed of light. Nope, this is exactly equivalent to how you would account for a one-way timing difference. Wayne goes through here and shows how you can derive the Sagnac effect in GPS. Where's rules? Now, the interpretation of the Sagnac effect with the range measurement equation. So basically, just by setting some integrals, he accounts for the entire thing. There's no difference in c plus or minus v in this equation. This is exactly what it represents. That's what he shows him. And then he goes on to show how you can, there was an around the world GPS experiment where they sent this signal through different clocks that was relayed, or different satellites that was relayed. And they showed the Sagnac effect in space, quote unquote, right? Like for some reason, Earth rotate is affecting the clocks. Anyway, what he shows though is that you can derive the timing difference just from the same thing. It's equivalent. So it's c plus or minus v. And is there anything else anyone wants to add? I know Taylor had some stuff.
Yeah, so I was told before that we can actually derive curvature from GPS, which is actually how I started looking into it. And basically they say that things on the outer edge of the satellite receivers, like things that are further away, have like an unusual increase in time that it takes to from the signal to go from the satellite to the receiver. And they're actually attributing that to curvature. But whenever I was learning about refraction in the atmosphere, I was learning that radio signals are also susceptible to refraction. And in particular, like the propagation can actually be slowed down by things like water, humidity. I even learned that ions and plasma, NASA says there's a plasmasphere. Anything like that can actually hinder the signal from effectively propagating. But if you're just assuming the speed of light through the atmosphere, then you're going to have some issues. And especially if that signal's coming in from the side, you're going to have even more propagation as it goes through more atmospheric layers. As it's not going vertical, it's going through more atmosphere to, reach the satellite, or for the satellite to reach the receiver. So this just makes so much sense. I'm like, okay, so there's even like a tropospheric correction, because they acknowledge this, but I'm just skeptical to say that this timing delay would be like some, cause a curvature and stuff like that. I just thought was absolutely ridiculous. And then as I started reading into it and reading some of the geodesic books, they were talking about these behind the scenes calculations that go on, which is just beyond hilarious. Why do they have to be behind the scenes? Why can't they be transparent? And then, people that we talked to that actually have worked in the satellite field, they're under strict oaths not to say anything about it. I don't know. It's just very peculiar. I just think they should be more transparent about all the calculations and corrections they're doing. And we should try to think of what other things could cause a signal propagation delay. And especially if we acknowledge that these things, literally like humidity and things in the atmosphere, could slow down radio signals. And as you're going through more atmosphere, shouldn't you expect more? Yes. Then why would we attribute that to curvature automatically? I don't know. It's just something to take into consideration, and that we definitely need to isolate more in order to say, yes, this is definitely from curvature instead of anything else. And apparently, the timing delay is really minute as well. So it's I don't know. I just don't think it's definitely not good proof of curvature.
Yeah, I mean, with all the back end corrections, it certainly can't be that we're not even privy to. We can't certainly say that it's reliable. And if we had to, if you really wanted to, right, it's like we would have to call into we'd have to bring a satellite down, examine it. None of these things are things that we could do independently. So proposing that as mutually exclusive proof and then walking away from it is just disingenuous at this point, because we have, in plain English, this being discussed and talked about, how these corrections occur on the back end. And now we know what the corrections are, what it means to correct. What are they correcting? How are they doing it? Well, it's timing with respect to the speed of light. They've mapped out the entire world, and they know, right? They know what dimensions they need to have for the model, right? Is there now? Here's the thing: it's like because the timing differences match up. Does that mean that that's what they measured? Is that like no? Not at all.
Yeah,
Oh,
they're
yeah,
using,
and
they're
eventually,
correcting it.
They
yeah. And I forgot this last point about the Z position. And the Z is like the altitude, and that doesn't automatically give you a readout. I was learning this because I was like, okay, well, how can they actually test for curvature? At first I thought, okay, well, the GPSs are able to see like the altitude, but no, they have to use post-process calculations in order to get the altitude from the X and the Y. And that's kind of some of the notes that Alan went over at the beginning, how they'll literally compute that Z axis, which is your altitude. And they have to like there's the older and the newer satellites actually do it a little different. I'm not pushing that note in there, but basically they'll have to put it onto an ellipsoid model in order to see, the altitude at that location. So they're not like automatically deriving it from what I've
are
heard.
you telling me they need to use a reference ellipsoid to do their timing differential
Yeah, and
for
yes,
what it would have to be, and then cross referencing that with two geoidal potential models, and then using a uniform correction at any latitude and longitude? Nice.
yeah, like all the coordinates literally are on,
So
assuming curve.
yeah, so real quick, by implication of the uniform gradient correction, right? Because if it was asserted by them how they've surveyed out and
You
applied
literally have,
corrections,
yeah.
you're lagging really hard, Taylor. If their corrections were as asserted, right, there would be differences that are accounted for, but they use this uniform gradient. So what's the implication? The implication is that they're at the same altitude elevation from us at all times, or like, they're at an equidistant relationship to us, meaning, they're not taking an elliptical orbit where they're going to have a perihelion and aphelion, uh, where like that gravitational potential is going to change, because otherwise it would have to. It means like they're moving uniformly above us at an equidistant distance.
Yeah, so here's a little note that I had, that the Z coordinate is not measured directly, but is computed as a part of the 3D position solution from raw GPS observables. So they're literally having to get the Z data afterwards. And, then you have to question, okay, well, are they having to assume curvature in order to get that? Then like an altitude readout would say, oh, this altitude shows that like we're curving. Like, okay, so what post-process calculations did they use to get the Z position? If they're just going to use that as evidence,
Yeah.
which they acknowledge that they do. And we even saw that in the Geodetic book in the beginning that Alan showed some of those notes, and the link should be underneath them in that screenshot that I shared, if you would like to share it. And if anybody else wants the link, I could share it with you.
All right, and I guess we'll read this real quick. So this is from Daniel Garzi. He's talking about 5 different predictions that relativity was supposed to make that haven't come true or been manifest, and actually some that falsify it. So he points out here that regarding GPS in 1997, Wolf and Pettit to test the isotropy of the one-way speed of light by analyzing GPS satellite network timing signals from a database. Right. So remember I said that from SV to ground receiver, right? That's a one-way measurement based off of the timing difference because they're starting with the reference of an absolute timeline from GPS time. They have the assumed speed of light, so they can measure. They have their how much they have their elevation difference calculated, so they know what it should be. Right. So they're like, well, let's look and see what the one-way speed of light is here. And they found no dependency on the source to receiver motion, which they interpreted as evidence that the speed of light is isotropic. Oh, well, I guess they found it, boys. Maybe those timing differentials are right. Maybe it is a geoid. However, Wolf and Pettit noted that the data set that they had analyzed had been preprocessed and corrected for the Sagnac effect. Oh, shoot. Which is a first-order change in the time of flight of radio signals between satellite and receiver. And justified this correction by claiming that the Sagnac effect is a relativistic effect that was to the second order in V over C. That's not true. If it's directly proportional, it's V over C. That's not dimensionally consistent with the effects of relativity. Relativity is a product of, like the length contraction and time dilation is a product of the square of velocity over C square, not V squared, or not V over C. So anyway, and therefore they, oh, go ahead.
I was say, don't you like how they say, in this case?
Right.
Like, not in all cases.
Right. And so, you're right. The special case, dude.
It's just a special case. Yeah.
But this correction was made in the first order of a velocity component in the line of sight between each satellite and ground receiver in the ECEF frame. Uh-oh. So quick refresher, the ECI frame is a fictitious frame at the center of the ball that's stationary, non-rotating. The ECEF is what they call the lab frame. That would be the Earth frame. That would be where you're at on Earth. The ground receiver on Earth is not supposed to have a first order timing difference based on his velocity. That would mean that you could use the speed of light to measure absolute motion. And if you could measure absolute motion, where's my Michelson and Morley 30-kilometer velocity fringe? Right? Where's my orbital correction for the atomic clocks when they're parallel and perpendicular to the velocity component of Earth around the sun?
That's to be linear motion too, right? Because it's point to point between the receiver and satellite.
Mm-hmm. Yes.
Dang, so they correct the point to point signal based on receiver motion?
Yep.
That's like GG on its face.
On its
Yeah.
face.
Can I read this quote real quick?
Absolutely.
This is actually from ESRI. So I just made it to my car, so I hope I can sound better now. So the ESRI is the Environmental System Research Institute, and they specialize in geographic information system software, location intelligence, and mapping solutions. Known for mapping. Basically, they do a lot of mapping stuff, geodatabase management across. Yeah. So anyway, they do a lot in like making these maps apparently. And so let me just read a quote from them. This is called Mean Sea Level GPS and Geoid. And here's the quote. It talks about the GPS receivers can provide only the ellipsoid geometric height. Consequently, newer GPS devices output orthometric geoid height measurements as a product of quote unquote behind the scenes calculations based on a combination of formulas, tables, and matrices that the geographic coordinates as inputs. And then it says the appropriate height for the geographic location is taken from a coarse-refined DEM matrix is provided instead of a real measurement of the Z value or height. And then some receivers use approximations of the geoid height to estimate the orthometric height from the ellipsoid height. So other units based on older technology provide the direct readings of the Z value based on the ellipsoid. So this is a segment I just put in the chat with the link as well if you want to go read it from the ESRI website as well. If you want to.
Hey, Taylor.
Yeah, go ahead.
Alan actually presented that text in his presentation.
Okay, well, I
now.
just wanted to double down on it. I just I don't know. I was very interested when I found that quote. So
Fair enough.
Yeah. All right. So does anyone have any questions, comments about that?
Nope. Good shit. Well, for me.
Yeah, I do. Bart Bardington here from Moose Knuckle Tribune. Alan, would you say you have lost brain cells after talking with McToon and debating with the Globy McLeplace? Or
it wasn't so bad.
do you feel Was it worth it?
Yeah, it was fun.
All right.
They
Well,
show how
never.
foolish they are. All they have is insults.
Well, bad bear. Bad.
Every
Stay
now
out.
and then, you just have to double check real quick and see if there's actually any evidence of the globe. Like maybe we forgot one. So it's nice to go back and see that there isn't any that doesn't make any assertions, that
Yeah, but
can't be
you don't
falsified.
check in the trash can, bro. Like you're not
Oh,
gonna find anything in there.
I mean, I've looked everywhere else. It's hiding. If it's not in the trash can, then it's nowhere. It's the
Well,
last
it's
funny
place.
when it's funny when
not.
people ask like, "How are you still? You're still a flat earther? You're still into that?" Yeah. There hasn't been any real evidence presented for the globe.
Well, it's not
So.
gonna come from McToon. So
Yeah, and then the celestial theodolite's just that's a straight GG.
Yep, and there will be a Cell Theo update on Monday, so be sure to stay tuned for that. I know Jesse and the Blads are very excited.
Yeah, they keep bringing up the same argument. Let's ignore the other 36 observations. Let's talk about these two that need to be redone.
Oh my gosh. Well,
All right, well, let's not mock them while they're not here. Otherwise, we'll have to allow them to talk to us and stuff, and we can do that
Oh, yeah,
Monday
my bad.
instead of
See you
Saturday.
Monday.
Yes, Monday.
thank you. Thank you, Alan, for this wonderful presentation. Yeah, you did a wonderful job presenting all data.
Well, thank you, Taylor, for finding those awesome back-end corrections. That's a great supplement to the argument, and really, in plain English, tells us that if you're using GPS to quote unquote verify where you live, it's a reification fallacy, right? And you can't independently verify. Like if you even believe that the speed of light is constant, you can't even verify that, right? But like assuming you can't even verify the corrections, the positions of the satellite, etc. You couldn't call it into if you had to, if you had to go to court and like prove some stuff, if you really had to, you couldn't bring anything into question, or you couldn't evaluate anything that you would need to prove your point. So using that is not a good argument, and that's why we like the celestial theodolite a lot more, because all it requires is timing and the position, you to reference the star at the angle of where it's at relative to the angle that you calculated for whatever you're using to occlude it. So it's a much cleaner
No sketchy
way.
post-processing calculations.
Right. All we have is a timeline and how fast something moves in the sky. That's all we need to know. Great.
Hey, great presentation. Thank you. My hunch is, there's probably tons of engineers and various technicians that work in fields like the satellite and whatnot, in the various like space related technology fields where they have a hunch and, they probably have some kind of physics, common sense proof that there is no curvature, there is no sphere, there is no motion. But sadly, none of them can say anything because their livelihoods would be at stake. So I just find that tragic. I mean, I can understand, young people with families to support, why they wouldn't come out in public and just tell us the truth. But the truth has a way of leaking out. So anyway, but I just think it's tragic.
Well, I'm so glad that you brought that up, because that's actually, we did a tribute to Ron Hatch last Tuesday for the Ether Cosmology Roundtable on Tuesday, episode 82. It was a tribute to Ron Hatch's work, who was in the GPS field, and he realized, very quickly that relativity was what was wrong with GPS, and to fix it, you had to fall back on the classical mechanisms and equations that describe c plus or minus v, rather than the constancy of c and the assertions via Lorentz transformation. So without getting too much into the particulates of relativity theory, right? But if the theory is true, there has to be a specific way that light and relative motion is treated, and it has to be done via what's called a Lorentz transformation. And none of that is present in GPS code or the infrastructure on the back end. And this is so we have a reference here from 1995, an engineering overview, GPS and relativity, an engineering overview. And this is basically like Lily was just saying, a bunch of engineers were like, hey, where's we got this system going and we're supposed to be accounting for these different relativistic effects, but we're all out of effects to account for. Everything's working fine. Where's the relativity? Where do we put it in at, Captain? So they go on to say here that basically the effects of special and general theory cancel each other out. So the clock runs faster at lower gravitational potential, but it also retards proportional to the velocity. So they're saying that the corrections that accumulate over that basically cancel each other out for special and general theory. So this is a memo that was put out to kind of pacify these engineers that were like, hey, what's going on? So he says here, hey, look, there's no need to do Lorentz transformations or anything like that because the gamma factor only changes the result from the classical by 2 to 3 millimeters. And so we're still good within spec. There's nothing, the reason that it's not that there's no relativity here, guys. It's that the terms cancel each other out. So that's cool. So you could show how much gravitational potential would be corrected for. You could show how much the velocity correction would be accounted for. But they're saying that the effects cancel each other out. And they don't even need accounted for. And then we have down here at the bottom a note from Carol Alley, who 17 years prior to 1995 did an atomic clock experiment similar to the Heffel and Keating experiment. They measured a one-way time dilation, in other words, the Sagnac effect, not time dilation, through atomic clocks, and they attributed that to relativity. And they said, hey, relativity now has to be included in engineering. It's no longer just the magical theory of astronomers that they use for funsies. It has to be an applicable technology. So here we are 17 years later, Carol Alley is writing in, and he's like, hey, we finished the all the corrections that would need to be done. Why aren't they in here? Why aren't we using Lorentz physics? He says, let's see here. And if one perhaps does the explicit recognition of the special relativistic effects, I mean, it took a long time to get general relativity down properly, but I think it's more or less correct now, he hopes. But it's the absence of the explicit acknowledgement of special relativistic effects due to the speed of light being the same whenever measured by an observer, leading to the relativity of simultaneity in the associated Lorentz transformation physics. There is nothing of that modeled in the current system, and I think it should be. Now, this is pretty crazy and damning because if relativity is true, right, if you have an absolute timeline, right now, an absolute timeline is kind of an abstract concept, but if you have a synchronized clocks all around the world that everything is referencing, well, you now have a localized absolute timeline, right? So in that context, you now have this absolute timeline. Now, if you're taking measurements with the speed of light between observers that are in relative motion to one another, right? If one lab's stationary and one's moving, well, you're going to get differences of simultaneous events. So if two GPS stations or vehicles are sending out signals and an observer in relative motion to another one receive their signal, right? The event in which the signal was sent would have to be a physically different time based on the relative velocity of at least the moving observer if the Einstein train analogy is true. Yet there's no back-end corrections to adjust the time of flight for the receiver in motion that would correspond to that disconnected simultaneous event. In other words, this localized timeline is correctly is showing that simultaneous events that occur within the timeline are absolute. They're not relative. If they were relative, the GPS receivers would have to make a back-end correction to adjust the timing, because instead of getting the time when it was actually sent relative to a stationary observer, it would actually be sent at a different time, later or sooner, depending on whether or not they're moving towards or away from one of the stations or SVs. And that is a catastrophic failure of relativity theory. Right? The whole premise of the constancy of C leads to the relativity of simultaneity, which leads to relative lengths and times. If there's no relativity of simultaneity, then length and times aren't relative. So that's a huge implication there. And this guy was previously saying that, praising the experiment he did as proof of relativity and how it needs to be incorporated and how super true it is. Now he's begging for it 17 years later to be incorporated. Kind of sad when you think
Yikes.
about it.
Yeah. Just let it go.
It's like just a
Okay,
heads
so
up.
Alan, I do have a question for you.
What's up, Andrew?
So, at what point of information and experience would you be accepting to the point where they would be able to, like McToon, as an example?
What?
Like, at what point would you say, okay, I was wrong, and that evidence is actually correct that they are presenting?
Oh, they would have to show Lorentz transformations for relativity of simultaneity. They would have to show, that alone would be good. That'd be huge. They could show reciprocal time dilation, right? That would be evidence that I was wrong. If you could show that a stationary clock retards proportional to a moving clock, that'd be dead wrong.
Reciprocal. Yeah, talk to Jesse about that one. He loves the reciprocals. But either way, I'm only asking this as a general open-ended question. And I do agree with you in pretty much everything you're doing. So I'm just putting it out there.
Nice.
Because I like to be proven wrong. And I think a lot of people do as well. But a lot of people don't.
Yeah, it would be nice to be proven wrong. Unfortunately, I cracked open the actual GPS manual, and it literally says that the speed of light difference is deriving the proportional velocity to the receiver. So I don't know. It's like it's hard to be wrong at that point, right?
It's pretty tough. Yes. But either way.
But yeah,
I am.
And another thing they do is the transformations between the ECI and the ECF, right, are done with the same time value, the same time coordinate, which is another relativity, no. So they shouldn't be doing Galilean transformations. They should be doing Lorentz transforms. They don't do that either. They use an absolute transformation for this, meaning absolute time and distance. So, like, to falsify that, I mean, they'd have to show me some Lorentz hanging around somewhere. Some simultaneity corrections.
just hanging out.
Just there, like if I crack open my GPS receiver, there has to be a little Lorentz in there, doing something, breakdancing or something.
Yeah, that's a weird. Oh my gosh, I am working on like 3 or 4 different types of presentations. I'm going to be doing again, like part 2 and part 3 of some of them. But yeah, I think, Alan, what you're doing is really, really awesome. It takes a long time to actually do this. So I tip my hat to you, sir, for doing this.
Andrew, I realized figuring out what GPS is in relativity is a lot like making trivia questions. It's the same.
Really?
It's the same concept. Figuring it all out and researching it. Like this is the same way you like to do that. It's like little trivia.
All right. Well, I think that Kat had said that she wants to do another little tiny private conversation with the 3 of us about what's coming up. But either way, that's going to be up to the 2 of you
Maybe we should wait
And
till
I'm gonna
after
just
this
sit.
presentation.
Cool. Well, we're in a presentation right now,
Sorry.
so that's kind of.
Yeah. I'm interrupting. I apologize.
You're good.
Please, sir, continue.
Jesus, Andrew.
Shut fuck up, man.
All right.
Come on, Peter.
Love you, bro. Good presentation, Alan.
Thanks.
Everyone should check out the Ether Cause Shop. I'm about to buy my lifetime membership hoodie right now, bro.
Oh, you about
tip
the
money.
about the cop?
Where's the rest of the EA crowd? There's not many of them here. There's a lot of
Well,
Keith Cosmology people here, but where's the EA crowd?
Stone, didn't you hear the news? The new number one, like almost no one comes to Alan Relativity Prezzies to defend relativity. And number two, there was a great rift, and I think everyone's the globularist regulars are hanging out somewhere else right now.
Oh, there was an exodus.
Yeah, there was a shift in momentum, and there's a periodicity to it, so they'll be back.
Yeah, all right.
But yeah. All right. Well, thanks for coming out, guys. Much appreciated. I hope everyone was able to get something useful out of this, maybe learn a thing or two. If you have any questions, please feel free to send me a DM or tag me or whatever. I'm going to go ahead and wrap up. I'll be right back while I roll the intro or outro. All right, lads and ladettes, see what's going on in the YouTube chat. Shout out to the boys out there in the streets. See my boy Ion, Bogan, Tony Coriolis, Shalom. The boys, Joshua. My boy DA, who just got slayed by Shalom. What did he get slayed for? Ion's cat. Tune destroy. Oh, this is anyone with a brain. Yeah. The space progress. Nice, dude. Well, I hope space progress proves to be wrong. That'd be super dope. All right, let's see what else we got here from the boys. All right. Looks pretty clean. All right, well, thanks again, everyone. And the support that you guys have shown, thank you very much. You guys absolutely crushed. The hoodies, again, are going to be limited edition. The print for those, the ability to buy those and order those ends on Tuesday. So get those before the limited run ends. And then shirts and hats will still be available after that, though. So thank you guys for the support. It's been awesome. We are going to continue to grow and build this together. Oh, and also if you're not already on Discord and you bought something or whatever, you want to be a part of the community now, you're getting in here, you're getting your feet wet, right? Hop in Discord. I will post a link on the coffee, what do you call it? Like the coffee blog thing or whatever. There'll be a thing there. So if you're not familiar with Discord or whatever, there's a phone app on your respective Android or iPhone devices. Come and get acquainted with the community here. All right. See you guys probably tomorrow. We'll figure out some. Oh, yeah. I'm going to do something tomorrow. There'll be a Prezi somewhere about relativity or something. And then Monday and Tuesday will be Celestial Theodolite and a presentation by Shane to close us out for the end of the merch sale. See you guys tomorrow.